So is your bounds, I mean, that's a really nice idea. I was just wondering, is it tight for any particular family of distributions?
Um, I mean, obviously it will be tight for
Exponentials
IRM.
or yeah, for IRM.
And,
So yeah, so maybe the question phrased differently would have been, do you have a sense of if I put additional conditions on the hazard rate, so if I know it's monotone or something of that sort, is there a hope that it's tight?
I don't think so at present because because the even if you say it is monotone, let's say increasing or you have an increasing or decreasing hazard rate, then also the way we propose the bound here is basically we are trying to maximize the aggregate hazard rate in the cache. So you can say that. Okay, let me share this. Maybe this will give. I
I see
have
your
a
point. So you're saying when you have the sum of the hazard rates, so maybe if they were correlated in some way, there would have been a hope, but
yeah. So the
okay.
overall goal is to maximize the aggregate hazard rate in cache.
Okay. So Rahul Vaze has a question online which he wants to just ask directly, and Gary Williamson also has a question on Slack. So maybe I'll ask Rahul first. So
Hi,
Rahul, go
Nitish.
ahead.
So this is Rahul Baze. Nice talk. I missed something. Why are you worried about an upper bound? Because for LRU and all, we can actually almost up to constants, we know exactly what the worst case bounds are for both LRU, and then there is something more complicated, which is called the marking algorithm or another version of it. So up to a constant 2, we already know both the lower bound and the upper bound. So what exactly is the objective here?
So when you say you have an upper bound for LRU and similar policies, is it anticipative or
So
I mean,
on
depend on
It's
the
a
traces?
no, so
it's a
on,
worst case upper bound,
yeah, in the
multiplicative
worst
worst
case,
case.
what we know is that it's essentially log n, where n is the size of the cache. And up to 2 log n, you can actually, so the
Yeah,
lower
but
bound is log n and upper bound is 2 log n. And there are better algorithms which can, it's more complicated, but get very close to the log n. Now here, what exactly is the objective function is something I missed. What are you trying to do?
So this is an upper bound on all non-anticipative prefetching or non-prefetching based policies. So the policies other than the recency based policies, I mean, for the frequency based policies and every other policies other than the LRU policy, this bound is valid.
Okay, maybe I'll send you an email. Something is missing. So.
maybe to ask to say one thing on behalf of this paper, those the multiplicative bounds need not be tight for many families, and like you may be able to get like say much stronger additive bounds, and we often wouldn't know if we don't have good upper bounds for doing that. So like what would be awesome is if this could be used to get better additive bounds, let's say for specific families of distributions. So you're right, the multiplicative bound exists, but that's not necessarily the best thing.
But yeah, at least for ZipF, we know something.
Sure. So for other families, we know better things, but I guess the hope is, can this give us better generalized bounds for other families?
And also we have very minimalistic assumptions. Like you only need to have the hazard rates defined at any point in time for all the objects. They need not follow any particular popularity distribution such as zip or not. So
Now,
the
does
only
it final answer, does it depend on the size of the cache or not? Is the hope that you can get away with the dependence of the size of the cache? Is that the hope?
no, it does depend on the size of the cache.
And what's the function? Logarithmic or sublogarithmic?
It's algorithmic actually.
Yeah.
Okay.
Yeah, I mean, I guess you have to this hazard rate ordering and then check.
Yeah, maybe for some particular cases we might get a form of logarithmic or not. I'm not sure, but generally it's algorithm.
Okay, Carrie has a question. Carrie, are you sure you don't want to ask it online directly, or okay, maybe I can repeat the question. So the question is, so Carrie's curious that why the results on the IBM trace give very similar answers for Bellardi and the hazard rate bound, while it was much tighter in your first simulation. So I guess this kind of is related to what I was asking. Is there anything special about the distribution in the IBM trace versus your simulation that you saw these sharp differences?
So even in my other simulations, which I have not included in the slides, based on the monotonicity of the hazard rates, I did find different results. For example, for decreasing hazard rate, the distributions following Pareto, request process following Pareto distributions or such, I did find the upper bound to be tighter than the Bellardi's algorithm. But for the case when it has an increasing hazard rate, for example, for uniform or other distributions, I did find Bellardi to be tighter than the proposed upper bound. So it's not that our proposed upper bound is always tighter, because Bellardi is a non-prefetching based policy and our is a prefetching based policy. So in some cases, we do find that Bellardi is tighter because we are allowed to, prefetch as many as B contents, where B is the cache size. So it's natural that we'll be getting higher hit probabilities. So because of that, in some cases, depending on the monotonicity of the hazard rate, we do get performance so we do get results that are less tighter than the Bellardi's result. So does that answer your question, Carrie?
Maybe while
Thank you. Yes.
Awesome. One other quick question then. Did you actually try testing out with correlated arrival processes?
No, we haven't yet. I mean, for the real world traces also, we actually fit to a generalized Pareto distribution, assuming that they are not correlated. But yeah, that would, so then for correlation, we have to, our model does capture that the algorithmic upper bound the proof still holds for correlate some kind of correlated process where you assume conditional independence given the history of the request access patterns. If they are conditionally independent, then the bound still holds, but we haven't tested it on any real world traces with correlation.
I mean, like a natural thing I would think of is something like a Markov modulated process, where that would be really interesting if we had something.
I mean, we can actually, we did give it a thought, and we can actually get a closed form even expression for hit probability bound for the MMPP process.
Right. Other questions? Okay. If not, again, on behalf of everyone, I will applaud the speaker, and actually a round of applause for all the speakers. Thanks to everyone else working in caching, this session went off pretty well with minimal issues.
So, okay. Thanks a lot also from my side. I think the session was very, very interesting. Now, if you want to talk and discuss more with the authors, I will create three breakout rooms with the name paper 1, paper 2, and paper 3. And of course, I will put the authors in their proper room, and you can ask me in which room you want to join, because I can I need a guidance because there is just a random algorithm. So you type in the chat in which room you want to join, and I can put you in touch with the authors. Okay. So thanks, Sid, for managing the session, chairing the sessions. Thanks a lot also for all organizers.